Hello, everyone. Welcome to all the latecomers. Maybe we'll give a moment while everybody straddles in. So my name is Devon, and today I am really excited to be back talking in front of live people again for the first time in 18 months. It's very, very nice. And I'm also really excited about what I'm going to cover. There are a lot of things in this talk that I find extremely cool and extremely fun. I hope you all will as well. But let's just get right into it. The gist of today is that we are going to take a process that is normally parallel, so something happening in parallel, and we're going to try and make that distributed. Okay? You may have heard a saying before, something along the lines of when you have true parallelism, you get distribution for free. The theory goes that if things are happening in parallel, that it doesn't matter if they are happening on the same machine or on two different machines, that it shouldn't make a difference. But that's all theoretical, right? What I want to do is I want to do a real-world example. I actually want to walk through the process of taking something that is currently running in parallel and seeing how free that distribution is. And our real-world example that we're going to use today is something that I certainly hope many of you are very familiar with, and that is ExUnit. ExUnit lovingly runs our tests for us asynchronously if we tell it to do so. And it actually not only runs them asynchronously, but truly in parallel, assuming you have a machine with more than one CPU core, that is. But what we're not going to cover today, there are a couple things we're not going to cover. We're just going to sort of hand wave over it and just assume that it's there and working. And the first of those is actually creating or joining a cluster. Clustering and distribution in Elixir and Erlang, that's a talk all on its own. Right? There's networking involved, there's different libraries, there's a lot of security stuff you need to think of. We're not going to touch any of that. For today, we're just going to assume a cluster exists. That's just for simplicity's sake, and also because that's not really the cool part of what I wanted to go over. Also, for a lot of the code that we're going to look at, it's not real code. It's somewhere between pseudocode and like summing some code up and just getting rid of some other stuff that isn't important. We're basically just getting the gist of what's actually there, because we're going to be looking at some examples of real code, but the real code that I'm going to show isn't actually what's in the library, but it is working code, so we're going to read it. It's just sort of simplified or abbreviated versions of that code. Right, so first, before we dive into this, we need to learn a little bit more about how the parallel thing works. So how does ExUnit run our tests in parallel at the moment? ExUnit has a runner. It is in a conveniently named module, ExUnit runner. And it even has a public function called run. So I think we can all agree that hopefully this meets Sasha's rule of clarity. Like we know what's going on here at this point. It also has a couple other functions. It has that loop function there, which has two clauses, async and sync. I bet we can guess what's going on there as well. And then it also has a run module and a run test function. Again, probably also pretty clear. Digging a little bit deeper, again, the entry point to this is that run function. And we don't really care about what happens before it calls that loop function. And honestly, for today, we don't really care about what happens after. A lot of stuff happens there because ExUnit is incredible and it does so much for us. But it's not important to today. So really, what we want to know is that when it starts running, it enters that loop. And it starts with the async clause of that function. And this is a little bit more where we want to look at what's going on, because this is where the real magic is happening. This is where the parallelism happens. So we have this loop function, and what it does first is it just waits for a module, and it's saying it's waiting for an async module. This happens because the compilation of our test modules happens in parallel, asynchronously, by a different process. And so our runner is basically just sitting there waiting for messages saying, hey, this module is ready to be run. Like these tests are compiled, you can run them now. And when it gets one of those messages, it says, okay, I'm going to go ahead and spawn off a process to run all the tests in that module. And then once it's spawned that off, it goes back into the loop. And it waits for more async modules, and eventually we'll spawn more of them off. Eventually, we'll run out. We'll have already started all the async tests that we have, and it will get a different clause from that waiting function, and then it moves on to the sync part of the loop, which pretty much does the same thing, but for our synchronous tests, the ones that can't be run asynchronously, that can't be run in parallel. We don't care about that stuff at all, so this is where we're going to end today. This is sort of the gist of the function that we care about. This is where the parallelism is happening. And it's really important to note that the unit of parallelism here is the module, right? Each test is run in its own process, but those tests are run sequentially. It's the modules that are run in parallel. Okay? That's an important thing to note for later on. Now, if you're like me and you like to see stuff in pictures, well, here's sort of what's going on in pictures. We have this one process up there. Red circles are sort of processes to me. So we have that one process up there, and that's our main runner, and it's sitting there waiting for a message. Then we have that other process that's compiling all of our test modules for us, and when one is ready, it sends it on over to the runner. The runner says, oh, great, I got something to run, and then it spawns another process and says, hey, you go and run these tests for me, please. And then it just does more of that. It sits, it waits. It's sort of the man in the middle waiting for stuff to run. And then when it gets something to run, it spawns off another process. And it says, hey, please go run these tests for me. And normally, when we do this, when we sit down and type mix test and hit enter, all of this is happening within the context of a single node. Now, when I use the term node today, what I'm going to be describing is a single instance of the Beam VM, the Beam virtual machine. This is the virtual machine that actually executes our Elixir programs. There is a technical definition of a virtual machine that I don't know because I don't have one of those fancy university computer science degrees. But I like to think of a virtual machine as a computer program that knows how to run other computer programs. So when we start mix test and hit enter, it boots up an instance of the Beam, which is the VM that Elixir runs on, and Erlang and Gleam and all these other great languages. It boots up an instance of the Beam, tells it how to run our computer program, and then starts running our computer program for us, okay? So that's a node, a single instance of the Beam VM, all right? Now today, we want to try and change that box. We want to say, okay, what happens if we take these processes and run them in one place, but then we take these other ones and run them somewhere else? This could be a different node on the same computer. You can do that. You can start 2 instances of the Beam, as many instances as you want on your computer. Or it could be a node on a different computer. Could be in the same room. It could be across the world. But we're going to try and say, how can we make that work? How can we separate these 2 things? So we've covered the first part, and now the second part, the distributed bit. How do we take something that's parallel and make it distributed? Well, in the definition of that loop function that we looked at, there was a line like this, where we spawn a process to run a module. So this spawns a new process on the same node, and this says, hey, go ahead, please run these tests for me. To make this distributed, well, we cut that and we change it to this. And that's it. Thank you very much for coming to my TED Talk. Yeah, it'd be nice if it were that easy, but it's not. But it actually kind of is, but it's not just that easy. But we'll see. Trust me, it's close. What's happening here is we're still spawning a process. We're just telling it which node to spawn that process on. We're giving it a node. That could be the same local node. That could be a different node in your cluster. At this point, we're just saying, hey, spawn a process on this node. It's almost the same as spawning a process locally with kernel spawn. And there are the same variations of this. You can pass it a module function arguments, or you can give it an anonymous function like this. Both work. But this is the most basic way that you can distribute work. Now, I said that we're going to be dealing in real concrete stuff, right? Not theoretical. This is still theoretical. If we want to deal in real stuff, we need some tests. And remember that the unit of parallelism in ExUnit is the module. And I didn't want to write a lot of modules. So we're going to do a little light, very light metaprogramming to just define 26 modules for us in a loop so that I don't have to write 26 files. And that's what we're doing here. We're just defining a whole bunch of modules with, example test A, example test B, etc., all the way up to Z. And then, of course, these are going to be ExUnit case modules. And each of these modules is going to have the same test because it doesn't really matter. And each of these tests is just going to be chewing through CPU cycles, right? So we're picking the good old classic Fibonacci, just calculate some numbers, do some number crunching for me. It's also a great excuse to show that lovely 3-line Fibonacci implementation in Elixir. But that's all this is. All it's going to do is for the numbers from 1 to 35, go through and assert that the Fibonacci number for that number is greater than 0. So it's useless as a test, but it's really beneficial in that it's CPU bound. There's no I/O, there's no database, nothing. This is purely CPU bound. So that means if we have more cores, it will go faster, guaranteed. So let's see. If I run all of these tests in series on a very slow computer I happen to have lying around at home, it's slow. 19.1 seconds to run those tests one at a time, right? If I make them parallel, then we're a lot faster, 62% faster. That's a big improvement. But these are our starting benchmarks, all right? This is what we're going to try and improve upon. Because again, in theory, if you have more cores, you need less time. You can just distribute that work evenly across the cluster, and it'll all be done faster. But now we have a question, and it's a big question. And there's a great answer to it, too. We're going to do something that we kind of shouldn't do. A lot of people don't know you can do this. You can monkey patch code in Elixir. If you're unfamiliar with that term, monkey patching refers to a technique to add, modify, or suppress the default behavior of a piece of code at runtime without changing its original source code, right? And a lot of people don't know you can do this in Elixir. You can. You totally can. But you know, funny enough, a lot of people do know this by another name, which is hot code loading, right? When you load code into the beam, when it's running, you're modifying or removing or changing or doing a bunch of things to a running machine at runtime. Without rebooting, you're not changing anything source code-wise, you know? You're just sort of changing the definition of a function at runtime. And you can do that. The way we're going to do that today, though, is not with hot code loading. We're going to do it the bad way. Because it's fun and it's cool and we can. So funny enough, when you do this, you see a warning telling you, hey, you're probably doing something you didn't mean to do. It's saying, hey, you're redefining this module. You've already given me instructions for this module, but you're doing it again. That's probably not a good idea. You might have made a mistake here. And this warning is helpful. I love that we have this warning. But the cool thing is when you think about how we get this warning. How does it know that we've already defined this module and we're redefining it? And to answer that, we need to look at one of my favorite parts of the beam, the code server. Now, who here has heard of the code server before? Okay, a couple people. Great. The code server is incredible. It is one of the things that makes the beam as powerful as it is. Without the code server, there is no hot code loading. There's a lot of introspection and stuff that you can't do without the code server. It is a crucial part of the beam, and it's really cool. So we're going to try and understand this a little bit more before moving on, because frankly, it's like kind of the most important part of what we need to do today. So you can think of the code server as essentially like a giant key value store, where keys are function names and values are instructions for functions. So if you need to do this function, that means do this. If you need to do this function, do this. And it basically works by modules. So each module has its own sort of little box in there, you know? And in that box, it has the information about the functions in that module. So it'll say, you know, enum all one, ARD1, and then it'll have some instructions to tell the virtual machine what to do, you know, to tell our program how to run our program. For the most part, it's like this. Of course, there are exceptions, but every function has a name in the beam. That's the way it works. Every function has a name, a unique name, even anonymous functions. When you define an anonymous function in IEX, you might see something like this, and you get, as the output, like function 45.40011.524 arity 0 in Earl eval expression 5. That's that function's name. It's saying what it is. It gives it essentially a random number, but then it also gives it a reference to the function in which it is defined. In this case, this anonymous function is defined within Earl eval expression 5 because that's how IEX works. But if you were to inspect any of your code with anonymous functions or anything, they all have a name. They always have a name. That's how the beam works. Functions always have names. And like we mentioned, each module has its own little box, right? Because the code server deals with modules. And in those boxes, we have information about the functions in that module. But really, those boxes also correspond directly to beam files, .beam files. So these beam files are instructions to the VM about what to do when it encounters this function. It's basically instructions on how to load our program into the VM, which is another computer program. So that really means, if you think about it, Elixir is a computer program to write a computer program for another computer program, to run our computer program. Like, it's really weirdly meta when you think of it like that. But beam files are really the thing that the beam cares about. It doesn't know anything about Elixir. It doesn't know anything about anything other than how to take beam files and turn those into instructions in the virtual machine. So what we need to do is remember that a beam file corresponds to a module, right? You always have one module per beam file, and that this stuff populates the code server with instructions about what to do when it sees a function. Okay, that's the important part of the code server. We'll get into how cool all of this stuff is later and like the stuff we can do to it, but we got to get back to the point at hand. We've got to actually make these things run parallel, or run distributed. They're already parallel. We got to make them run distributed, and to do that, we need to change the behavior of ExUnit. So we know we're going to monkey patch it, and we know we need to do that at runtime. How do we do that at runtime? Well, we can do it in a bunch of different ways. But first, we need to decide what we're going to do. So we have this loop function that we had before, right? Because this is where the parallelism happens. If we want to take that parallelism and turn it into distribution, we're going to have to change something here in the runner. So, well, what do? First, we get a random node in the cluster, right? So we just, this is a vast oversimplification. And, if you're playing along at home or here, you might say, well, Devon, that's actually not going to give you a random node in this one instance. It's actually going to give you the same node every time. If you know why that is, or you want to know why that is, you can talk to me later. But we're just going to pretend that this is going to give us a random node every time we call it, and that we're just going to do the most naive way possible of just letting randomness distribute it. And so we get that node, and then, well, like I mentioned earlier, we change spawn into node.spawn. And that's kind of it. So we know what we want to change now. How do we actually make the change? Well, we got to do it at runtime. We have to define these functions. How can we do that? ExUnit gives us a way. It's great about that. So we have our test helper file, which is a .exs file, which means it's compiled at runtime, right? So it's a runtime change. If we redefine that module in our test helper, then voila, we have changed the definition of those functions at runtime. We've effectively monkey patched ExUnit in this case. An important thing to note, not that you should ever do this, because you shouldn't, but if you do, you actually have to copy and paste the whole module. You can't just put in the function that you want to change or something, because again, remember, the code server deals in blocks of modules. So if you define a module as just the one function you want to change, it's going to get rid of all the definitions of all the other functions. So you have to define the entire module, because it's going to say, OK, you've given me a new ExUnit runner. I'm going to change this whole module definition out with this one that you just gave me. You can't just like tack on a new function to a module, unfortunately. Right, so at this point, we know what we want to do. We know how we're going to do it. Let's do it. Let's hit mixed tests, and we're off. But unfortunately, almost immediately, it doesn't work. And it actually doesn't work in a really awesomely confusing way, which to me is the sign that we're onto something cool when you manage to break something this badly. So basically what we have here is we have an undefined function error saying example test A ExUnit arity2 does not exist or is private. Did you mean ExUnit 0 or ExUnit 2? Excuse me? You just told me that ExUnit 2 didn't exist, but then you're saying that that's one of my options. How can we do this? How have we broken ExUnit this badly? And like immediately, the first thing we tried, and we just broke everything. Usually this sort of thing is considered a bug in Elixir, like bad error messages or confusing things like this. But because we are so far off the path of things we shouldn't be doing, I will allow it just this once. But I will just help you because it makes no sense. You can just stare at it all day and not understand it. But remember that code server I mentioned? Well, it turns out there are 2 of them now. So every node gets its own code server. So what we have here on the left, we have our local node in green. That's the one. We type mixed test. We hit enter. It spawns that up. And then the other one on the right, that's one of our remote nodes, one of the ones in our cluster. And what's going on when we run our tests right now is we have that one, and the local node says, hey, I got a test that's ready to be run, and it spawns it off to this other node. And this node says, OK, great. First thing I need to do is call this function, ExUnit underscore, double underscore ExUnit double underscore arity2. Hey, code server, can you give me the instructions for that? And the code server is like, no, I don't know what you're talking about. I don't know that function. And so it raises an exception. And ExUnit, being great, captures that exception for us, and then also does the nice formatting and like gives us that "did you mean?" That's an ExUnit thing. So the process running the modules is like, oh, well, I got an exception. I don't know what to do with it. I'm going to send it back to the runner so that you can format this really nicely for the user so they can figure out what they did wrong and fix it. And so now the main process, the local node, says, OK, I got an undefined function error. Let me format that really nicely for you. And so it says, hey, code server, what are all the functions in this module that you know about? And it returns all the functions in that module it knows about. And then it says, OK, well, it looks like you needed ExUnit 2, so maybe you meant ExUnit 2, because there are 2 different code servers happening. And at the point where we were running this, the code server on the left knew about that module. That module had been compiled and loaded into that code server, but it had not been loaded into the code server on the right. How is that? Like, how can we fix that? Well, normally, you do a thing called remote code loading. There's a couple different ways to do this. The first way that you can do it, which gets you 99% of the way there most of the time, is by setting what's called the code path. So the code path for the beam is one or more directories. You can have multiple directories, but one or more directories in which the code server can look for beam files. So if you say, hey, I need to call this function in this module, and it's not loaded, then the code server can say, OK, I know where to look for that. I'm going to go check these beam files and load all these beam files and see if I can find the instructions for that. You can set this at runtime if you boot the beam in interactive mode. There are 2 different modes, interactive and compiled. So most of the time we're in interactive mode. So you can set this at runtime. And usually what we would do if we wanted to do this is we would say on the local node and say, get me the current code path, because that's where all my beam files live. And that's what I need to put instructions into the code server. And then you can say, hey, I'll do a RPC multicall. That RPC module is an Erlang module. It's incredible. If you haven't looked at it, you should. So you do a multicall, which basically says, I'm going to execute this function on all of the nodes in this list. And we're just saying, node.list, which is listing all of the other nodes in the cluster except for the current node. So it's saying, on all of those nodes, please evaluate this function, code, set path, and the path. So this will tell all of the code servers in our cluster where to look for Beam files. But that doesn't work for us. And it's not going to work. Why? Well, let's remember that our test modules are defined in .exs files. EXS files don't get Beam files written to disk. They're scripts, you know? They're not really compiled. They're evaluated at runtime. So there's no Beam file there for these other code servers to use. Now, there's another way to do remote code loading. It's kind of similar, but you can do it sort of module by module. So you can use another function in the code module on the Beam in Erlang to say get object code, which is basically saying give me what would be in the Beam file for this module. And you give it a module, and then it will return you the module, again, the binary. So that binary bit is like what would be in the Beam file. That's the instructions for the code server about what to do for functions in that module, and then the file name. And then you would take that information and you would do another RPC multicall to say, hey, everybody, please load this binary. So there's the code load binary function. And you give it the binary, and you give it the module and the file name. But this doesn't work either, funny enough, for the same reason. That code get object code function only looks in the code path. So it only looks at Beam files. We have no Beam files. There is no way in Erlang to basically take one code server and copy it to another. You cannot get information out of a code server. What's in the Beam files is instructions about how to populate a code server. It is not the instructions that go in a code server. And there is no function anywhere in Erlang. I have asked the Erlang folks. They've confirmed it does not exist. That allows you to get information about a module directly from the code server. So what are we going to do? Looks like we're stuck here, right? But we're not. We're okay. So let's take a step back. Remember how I mentioned that our test modules are compiled asynchronously? But what are they compiled to if not to Beam files? Well, the way they work is they're compiled in memory. That binary that would be written to a Beam file is generated by Elixir, by the Elixir compiler, but then it is basically remote loaded, but locally, into the code server using that load binary function. Right? So we need to do that somehow. We need to essentially interrupt the compilation of the test files and change it so that it's not only loading that code on the local node, but on all the nodes in the cluster. Okay? Another cool thing, ExUnit has its own compiler. When you run mixtest, one of the first things that it does is it goes ahead and it starts the compilation of those .exs files that we need to compile, because we need to compile those and load them into the code server so that we can, run our tests. And I said that we wouldn't be seeing too much like real code, but this is actually real code. This is basically the real money of that compiler, where it does the work. It does a bunch of stuff to find which files to compile based on your configuration. But once it has those, it passes them off to the Elixir parallel compiler, and it says, hey, please require these files, which means compile them and load them into the code server for me, please. And then it checks to see if there are any compilation errors or anything. So this is what we need to change, because right now this is only happening locally, which means only the local node is getting its code server populated with our test modules. That's a problem. So we need to change this. And luckily, we can change this pretty easily. We just do this. So instead of doing it locally, we do another RPC multicall, and we say, hey, please run this function, evaluate this function on all nodes in the cluster. With RPC multicall, if you don't give it a list of nodes as the first argument, it will just default to all nodes in the cluster, including the local node. So this is going to go ahead and compile all of our tests for us on all of the nodes in the cluster. So at this point, our code server will be happy. It will have all its code that it needs. We can hit mix test again. We can run it, and wow, at this point, it works. Like, it runs. Now, I say it works with very big caveats, though. What we have done today so far is the simplest way of taking something that is parallel and making it distributed. right? But there is a lot more that ExUnit does beyond just running our tests. It would be very easy for me at this point to basically break what we have and have it have really strange behavior, because there's a lot of stuff that would also need to be changed and modified, because there's, in-memory processes, and you need to know how to send messages to those other processes on other nodes. So there's a lot of changes you would have to make in order to make it work. But at this point, it works. And remember how I said we weren't going to see too much real code? This is the other bit of real code. This is the other exact change that we had to make in order to do the distribution. It's just the compiler, and it's this. It's literally 5 lines of code to take something that's parallel and make it distributed. So instead of just saying spawn a process, or sorry, instead of just saying run module, we're now doing an RPC call to run the module. But now the most important part, how fast does this run? How much of a difference does it make? Well, we can go back to our benchmarks. So in series, the slowest it could be on a very slow old computer, 19.1 seconds. This is awful. I was almost asleep by the end of it. In parallel, 7.2 seconds, 62% faster, much better, still not good enough. But then I took that same computer, I hooked up 2 extra nodes to the cluster. One had 2 cores, one had 4 cores. Both of them were still slow. Like, one of them was a Raspberry Pi. But 3.7 seconds. That's not bad. That's 80% faster than running them in series on a single node, 48% faster than running them in parallel on a single node. If we took this and we had enough CPU nodes, we could get this down to the time it takes just to run a single test. We could run 26 of them at the same time. You could have this done in, 500 milliseconds. That's a 95%, almost 95% reduction from running them in series on a single node. So you might be thinking that this is the point in the talk where I announce some new library that I'm open sourcing for everybody, and that everyone's going to go home and use immediately to run your test suites in 5% of the time that you normally would. But that is not the case. You may have seen this sort of joke meme before about drawing an owl, where first draw the 2 circles, then draw the rest of the owl. What we've done today is basically draw 2 circles. Because the hard part of this is not making ExUnit work distributed. That's pretty easy. Yeah, we didn't do everything you would need to do, but I could do that in a day. The hard part of it is making your application run distributed. Right? Think of what we were testing. What we were testing literally didn't have an application. The function we were testing was defined in the test modules. To get an application to work correctly distributed is time and effort, and it's not easy, and most people don't do it. And if you're not going to do it, this is useless to you. It's pretty useless unless you have a bunch of tests that are just testing pure functions, and then sure, go ahead. You know how to do it now. You can do the bad thing we looked at. You've seen the code. There will also be an example on GitHub that I have up there that everyone can clone down and look at. And if you want a real example of seeing this work, you can do it. But you're probably not going to want to be honest. But before you start thinking that this is all a waste of your time, because you don't get to go home and run your tests way faster, we got to learn about the code server. We got to learn about how ExUnit runs our tests. We saw a lot of really cool things. To me, the code server is incredible. It is such an incredible part of what is already a hugely incredible piece of technology. The Beam is amazing, and the code server is one of the most amazing parts of it to me. It's what gives us so many of the great features that we love about the Beam. So I would really encourage you all to look a bit more at these 2 modules. I know they are Erlang modules, and I know some people don't love reading Erlang or reading Erlang documentation, but there are great things in there, both to learn, just to deepen your understanding about the Beam and how it works, but also things like if you want to maybe do something like this in staging to investigate some issue, and you want to sort of do your own monkey patching of a module in staging, but then you also want to clean it up when you're done, you can learn how to roll back your code. Because the code server doesn't just keep 1 copy of a module, it keeps 2. So if you want to load a new one and then roll back, you can. So if you want to mess around, there are so many things that can give you so many ideas of things you can do for introspecting your system and working with your system and really just getting all that you can out of the Beam. these things have a lot of value. I mean, there's also a function in the RPC module that literally takes just a list of functions, and you say, hey, please evenly distribute this work across some cluster of nodes, and it says, OK, great, I'll do that for you. And that's like, for so many people, a dream that can never happen. And for us on the Beam, it's literally a single function call. So take a look at these modules. There's great stuff in there. But that's it for me for now. Thank you all very much. That's the link to the example that I have. You can clone it down. You can run it. All that you'll need is in the test helper there. You can mess around. That also shows how the clustering is done, too. If you want to do that locally and actually set it up, you can do it for sure. So yeah, that's it for me for now. Thank you all very much. And I guess I have time for questions. Are we going to go over? Or?
Yeah, we have time for one or two. Does anyone have a question here? Come on.
What inspired you to try something like this? Is it related to your mutation testing library?
So it's partly that. Because I have a mutation testing library called Muzak, and in that it allows you to basically spin up multiple nodes, and so that you can run tests on multiple nodes at the same time locally. But the way that works, it doesn't do any of this. But really, this is more of a conceit, you know? It's sort of like a trick to just like looking at cool stuff in the Beam. It's a reason to explore. At one point, I did think that I would be able to do this and get some value out of it personally, because the application that I currently work on is distributed, like it is run clustered. It's able to do that. I could speed up our test suite this way, and so I looked at it because I think like many of you, have a bunch of just old computers sitting around the house, or like some of them not so old, and most of the time they're completely unused. And I was like, well, what if I just clustered them all together and then ran all my tests on them all the time, and then my tests will run in like 6 seconds instead of 60. But it's still not reasonable, you know? But that was sort of the inspiration. It was partly from Muzak, and also because I genuinely thought like maybe I can make my test runs faster when I'm working. So yeah.
Hi, thanks for the talk. Do you know maybe what's the rationale for the tests and maybe also the active migrations for them to be scripts instead of like regular EX files?
No, you'd have to ask Jose about that. I would imagine it's because that's not something that would get shipped. Like if you were to build a release, that's not going to be included in your application. It's separate to the application in a way. So like, in a way, it is a separate application. The tests test the application, and they're not part of it. But I'm just guessing you'd have to ask Jose or whoever. I would imagine that would have come from him, because that's an old decision. But yeah, I have no idea.
OK, the last one.
Hey, thank you for your talk. I'm not sure if I understood correctly, but the compiling was done on each node separately, right? It was not like the primary node compiled it and then you distributed the compiled version between the nodes. It was like each node did it on its own. I've noticed that you had to provide path to this code function that compiled it and put into code server. Mm-hmm. And I was wondering if it's possible to distribute compiled code between nodes, so each of them can be instructed by some central authority to do something, but they don't need to have the code locally?
Yes, it is totally possible to do that, but it's also more work, you know? You could compile all of the files to binary and then do an RPC multicall instead of saying run the compilation on every node. You can just say load binary, code load binary for these binaries, because there are a lot of functions in Elixir that will essentially evaluate a file or a string or something into the Beam binary that it would result in. But to me, it was just simpler and easier to say, like, yeah, just run the compiler on all the nodes. But yeah, you could definitely do it that way as well.
OK, thank you so much. Let's give him another round of applause.